Mechanical Waves, Part 3. Now I'm going to shift gears a little bit and run through and show you a little bit of vocabulary associated with waves and those representations, or for lack of a better term, the anatomy of a wave. These may be terms that you're familiar with. Perhaps you've studied some of these things before in a high school course or what have you. But I want to remind you of a couple things. First of all, period and frequency are terms that we've already worked with, and those definitions carry over. Period's the amount of time it takes for one cycle of the wave, and frequency is the inverse of that. Frequency is how many wave fronts are passing by a particular location in a given period of time. As far as the terms up here, trough and crest and wavelength, I can define those for you, but I'm going to do that. But I think it's easier to do that in conjunction with a graphic that kind of shows you what they look like. So I think it makes it a little easier to identify. And then we're going to go on and talk about a couple of other aspects here. We're going to be able to calculate the velocity of the wave, not the velocity of the particles in the wave, but the velocity of that disturbance that we've been talking about. And finally, a term called amplitude, that again is another term that I think is easier to explain by showing you a picture. And then finally, this relationship, which is called the wave equation, which basically states, based on these terms above, that the velocity of the wave, or the velocity of the disturbance, is equal to the wavelength of that particular wave, and we're going to see exactly what that means in a moment, multiplied by the frequency, or how many waves per second are passing through a given area. So take a look at this graph, because I think it lays out a lot of those terms, particularly the new ones. A crest is the term that we use for any maximum point in that wave. So the crest here is at the top. Here would be another crest, and finally this would be a third crest. If you compare that, at the very bottom, these low points are called troughs. And crest is supposed to give that sense of a top of a mountain. That's how that term was why that term was chosen. While the trough is like the bottom of the barrel. If you remember the word trough as a place where animals are fed, and it's just a big bowl where the food or the water or whatever is down in the bottom. That's where that term trough came from. It's where the wave bottoms out before it goes back to the positive side. The distance from the midpoint, from the equilibrium position, from the relaxed position, that's called the amplitude. The larger the amplitude, the more energy this wave possesses. And if you think about it, that means there had to be more energy put in. You had to make a bigger disturbance in the vertical direction to get a larger crest with a greater amplitude, and correspondingly a deeper trough with that same amplitude. And then finally, wavelength. And wavelength is literally that. It's the length from the point on one wave to the same exact point on the next wave. One wave cycle. So a wavelength can go crest to crest. A wavelength could go trough, if you follow it to the next trough. Or a wavelength can go from any point on the wave to the same exact point where the next wave starts that same cycle. So that's what wavelength looks like. And hopefully those graphically, it gives you a better sense of what those words mean than it would if I just gave you a definition without that diagram. So now let's take a look at mechanical waves and solving problems with these mechanical waves using that wave equation. So here's an example. Sound travels through the air at 343 meters per second. And we're asked to figure what is the wavelength of a middle C note, which has a frequency of 261.6 hertz. So if you go ahead and do that, okay, here's how you'd work through that solution. First of all, we're given the velocity, travels through the air, 343 meters per second. Note, meters per second is how we know that this is a value for velocity, and obviously that's something from the very beginning of the course. And the frequency is clearly stated as 261 meters per second. We use the wave equation. We're looking for the wavelength. That's what it asks for here. What is the wavelength? So if you solve this for the wavelength, and this is the Greek letter lambda, which represents wavelength, you can see we solve for lambda, v over f. We substitute in our values, and we get a wavelength of 1.31 meters.